Dear students, good morning to everybody. Today, I want to teach you the flash type, counter type, and the dual slope AD converter. In the previous lecture, we already learned the uh, successive approximation type ADC. Today, we will learn the first, that is flash type ADC. In the flash type ADC, there is only the comparators and the coding circuits and the resistors are used. The comparator compares the analog input signal with their particular reference voltages, and the output of the comparator will be at logic 1 or logic 0, and this will be coded through the coding circuit. Here we will use the priority encoder and get the specific binary output. In the simultaneous or flash type ADC is based on the comparing an unknown analog input voltage with a set of reference voltages. If there is a n-bit flash type ADC to be designed, then 2 to the power of n number of resistors should be used, and 2 to the power of n minus 1 number of comparators should be used. So suppose if there is a 3-bit ADC, then 2 to the power of 3, that means 8 number of resistance are used here, and the 2 to the power of 3 minus 1, that is 7 number of comparators are used here. This is the block diagram of the 3-bit ADC, and this is the reference voltage, and this is the input voltage, and the input voltage is compared with these reference voltages, and depending upon the output of the comparator, the coding circuit, that means priority encoder, encodes like 0002 111 for the 3-bit ADC. Now come to the operation. First, the output of a comparator is in positive saturation states. When the positive saturation means it will be at logic high when the input analog signal will be greater than the reference voltage of the comparator. This is a non-inverting type of comparator. So when the input analog signal is greater than the reference voltage, then the output of the comparator will be logic high. So and otherwise it will be in negative saturation, that means the logic 0. So when the analog input signal is greater than the reference voltage of the particular comparator, the comparator output will be logic high. Now the reference voltage of the first comparator. So first comparator reference voltage will be the 1R divided by 8R. Total number of 8 number of R's are there into the V reference voltage. So that means the 1 by 8 V. Here this is 2R, R plus R, 2R divided by 8R into V. Similarly, for this comparator, the total number of R is connected with the inverting terminal is 7. So the 7R divided by total number of R's, that means 8R into the reference voltage V. This is the voltage divider rule. Okay. So here we will get the reference voltage is 7 by 8 volt. So now, if the input voltage is less than the first comparator reference voltage, this should be the first comparator reference voltage, then the output of the comparator will be logic 0. So the all the comparators output should be logic 0 due to the analog input is less than their reference voltage also. If it is less than 1 by 8 volt, obviously it will be less than 2 by 8 volt, 3 by 8 volt to 7 by 8 volt. So the output of the C1, C2, C3, C4, C5, C6 and C7 should be 0. Okay. So all the output should be 0 and the encoded output should be 0, 0, 0. So now the operation. Now the table shows that if the input voltage is greater than 0 and less than V by 8, so all the output of the C1, C2, C3, C4, C5, C7 will be 0, because this is a non-inverting comparator. Okay, so this will be all at the zeros. So if this is all zeros, then the coding output should be 0, 0, 0. Now if the input is greater than V by 8 and less than 2V by 8, so that means the first comparator input voltage is greater than the reference voltage of the first comparator, then this should be 1, others should be 0. Should be 0. Okay. So all are the zeros. So that means 1, 0, 0, 0, 0. For the second time, if this is greater than V by 8 and less than 3V by 8, then what happens? Then these two comparator input voltage is greater than the reference voltage of these two comparator, reference voltage of these two comparator. So for this reason, it will be 1 and others should be 0. Others should be 0. Okay, so that is the 1, 1 and others are zeros. So as the priority encoder used here, so the priority should be given to the C2 due to the C1 is logic 1. So this is the priority. So the C2 will be encoded at 0, 1, 0. Similarly, for the sixth comparator here, so if the input Vi is greater than the 6B by 8 and less than 7B by 8, that means this condition is less than 7B by 8 and greater than 1B by 8, then all other ones except C7. So all are the ones except C7, because it is less than 7B by volt but greater than 1B by 8. So all the output of the C1 to C6 will be 1 and C7 will be 0. So then as per priority encoder, the C6 will be coded. So 1, 1, 0 as the output. When it is greater than 7V by 8 and less than V, the reference voltage, then what happens? All the comparator outputs will be logic 1. And according to the priority encoder, we will get the 7, 1, 1, 1, 1, 1, 1. So this is the basic principle of the flash type AD converter. From the table, it is clear that the logic expressions for the V3, V2 and V1 are complex due to their dependence on the 7 input variables C1, C2 to C7. Hence, the coding circuit is implemented using the priority encoder. This is very much important for the gate. Which type of coder circuit is used in the flash type ADC? That is called the priority encoder. What is the advantage of this? This type of ADC is the fastest because A to D conversion is performed simultaneously through a set of comparators. Typical conversion time is 100 nanosecond or less. The construction is simple and easier to design, but there is some disadvantages. That is, this type of ADC is not suitable for AD conversion with more than 3 or 4 digital output bits. Then 2 to the power of n-1 comparators are required for an n-bit AD converter, and the number of comparators required doubles for each added bit. Now come to the second type of third type of ADC, that is called the counter type ADC. Here we only use the one single comparator and the binary counter and the DAC. Binary counter is nothing but a counter which counts the clock signal, clock pulses, the number of clock pulses that should be counted by the binary counter. So if this is a n-bit binary counter, that means it counts 0 to 2 to the power of n-1. Suppose this is a 3-bit counter, it counts 2 to the power of 3 minus 1, 0 to 2 to the power of 3 minus 1, that means 0 to 7. So total 8 number of clock pulses. Okay. The counter type ADC is constructed using only one comparator with a variable reference voltage. The variable reference voltage can be obtained by the sequence of binary counter and a DA converter. Okay. So the basic principle of is that when the reset, this is a active low binary counter. When it is active low, then the binary counter resets to logic 0. Then we will get 0, 0, 0 as the input of the DAC, and we will get the similar analog voltage as VR. Okay. So now this, if the input voltage is compared with this reference voltage, if the input voltage is greater than the reference voltage, then the comparator will be 1. Then the clock pulse will be in AND gate with this AND gate. And if it is logic 1, then the binary counter starts counting. Okay. So this is the basic principle of the counter type ADC. Now we come to the discussion of the operation of this type of ADC. The n-bit binary counter is initially set to 0 by the reset switch, which is normally active low. Normally active low. Okay. Therefore, the digital output is 0 and the analog equivalent VR is also 0. This will be 0. So the analog output will be 0 and the output of the digital is also 0. When the reset signal is active high, when the reset signal is active high, when the reset signal is active high, the clock pulses gated through the AND gate are counted by the binary counter. The DAC converts the digital output to an analog voltage and it connects it as the inverting input to the comparator as the reference voltage VR. So now the output of the comparator enables the AND gate to pass the clock. If this is 1, then the clock will be passes through this AND gate and this will be logic 1. The number of the counted pulses increases with time and the analog output VR from the DAC is rising staircase form because this is a ramp of the staircase. When the clock pulse 1 come here, then this is counted as logic 1. When it is 2 second clock pulse, then this is 2, then it will be counted as 0, 1, 0. So if it is 3, then it will be counted as 0, 1, 1. And according to that, the VR will be set by this DAC and the input voltage is compared with this VR, and the output will be logic 0 or logic 1. So if this is logic 0 and logic 1, so then it will be counted. Okay. So the output of the comparables and DAC is a rising staircase waveform as shown in the figure. The counting will continue until the reference voltage VR equals and just rises more than Vi. Because this is 1, the clock will come to the through the AND operation, and the output of the AND is logic 1, and the binary counter starts counting. Comparator output when the reference voltage VR is equals to the Vi, then the comparator output will be logic low, and it disables the AND gate from passing the clock because this will be 0. Then the counter stops counting. The counting stops at the instance when Vi is less than VR. And at that instant, the digital output of the comparator represents the analog input voltage Vi. Then the clock is inhibited, the counter stops its progress, and the conversion is said to be completed. The number stored in the n-bit counter corresponds to the equivalent n-bit digital data for the given analog input voltage. So this is the counting sequences. It will be count to as 000 for the 3-bit, 0002, 111. Then it stops counting. In this ADC, the counter advances by 1 count for every clock pulse, and therefore the clock speed decides the conversion speed. Conversion speed is 2 to the power of n by f. N is the number of output bits and f is operating frequency. Normally, the time required to reach 1/2 of the full scale voltage is called the average conversion time. This is very much important for gate. So the counter type ADC is very simple and needs less hardware compared to the flash type ADC. This is suitable for digitizing applications with the high resolution. The conversion time is very long. This is the disadvantage. It is variable and proportional to the amplitude of the analog input voltage. Since the counter always counts from 0 to a normal sequence, a maximum of 2 to the power of n counts are required to convert a full-scale analog input voltage. Hence, for the n-bit ADC, the average conversion time is 2 to the power of n by 2. This is the average conversion time is 2 to the power of n by 2. That means 2 to the power of n minus times clock period, which can be very long for the large value of n. Now, if we come to the problem, then it will be very much clear. What is the conversion time? Suppose this is a problem for a 12-bit counter type ADC. Calculate the maximum conversion time if the clock frequency is 1 MHz. The maximum conversion time of a counter type ADC is given by Tmax is equal to 2 to the power of n minus 1 clock periods. That is the 2 to the power of n minus 1 by clock frequency. So Tmax is equal to 2 to the power of 12 minus 1 into 1 by 1 cross 10 to the power 6. That is 1 by f, 1 megahertz. So then we will get 4.095 millisecond. So this is the maximum conversion time of the ADC. This is very much important for the gate. For the gate exam. Okay. So now I want to teach the dual slope AD converter. Dual slope AD converter. Is it visible? Okay, okay. So now come to the dual slope AD converter. Why it is called actually the basic thing is that in this dual slope AD converter, the integrator portion is included here. One T-flop is included here with the counter type ADC. This is a counter type ADC, and this is the TP flop, and this is the mechanical switch. The first, why it is called dual slope? When the switch is connected with this V in, then one ramp signal or the ramp voltage will be produced through this integrator. This is called the negative ramp. And when the switch is connected to the minus VR, then this integrator produces the positive ramp. This is called the negative ramp, and this is called the positive ramp. So this is the dual slope. This is called the negative slope. This is called the positive slope. So here the two slopes are there. For this reason it is called dual slope. So in the dual slope type ADC, the integrator generates two different ramps, one with the unknown analog input voltage B in as the input, and the another with a known reference voltage minus VR as the input. Hence, it is called the dual slope. The mechanical switch connected at the input of the integrator, which is controlled by the TP flop. When the Q is 1, it is connected to B in, and when the Q is 0, it is connected to minus VR. Assume that initially the output of the TP flop is logic 1. It means that the input of the integrator is connected to analog input B in. First step. So the T flip-flop is the negative edge trigger flip-flop here, and it is triggered according to the negative edge of the MSB. That is called Bn-1. If it is a n-bit up counter, then it will count from 0 to n minus 0 to the power of n-1. Okay. So the bit should be B0 to Bn-1 as the output. So in other words, the output of the T flip-flop will not change until the Bn-1, the MSB bit Bn-1 will not be changed from 1 to 0. Okay. So the n-bit counter is clocked according to the clock signal and the output of the comparator. Because if it is not 1, then the clock is not ended. And if it is ended, then the output of the AND gate will be logic 1. Then the counter will start counting, otherwise not. So if the VC is 1, then the counter will start counting, otherwise not. So what is the value of VC? Now VC depends upon the output of the integrator. If the V1 is greater than 0, then the VC will be 0. If V1 is positive, then due to the inverting comparator, the output VC will be 0. And if V1 is less than 0, then the comparator output, inverting comparator output will be logic 1. So assume that the n-bit up counter is initially reset. So all are the zeros. So if the 4-digit decade counter is initially reset to 0000, then the ramp output V1 is reset to 0 volt. Why? If this is 0, then this will be 0. So then the T flip-flop output will be 0 or 1. Come to the latter part. Suppose the V1 is reset to 0 volt, analog input voltage is positive because this is 1. Okay, so the first, if this is 0 but it is not 1, because I already told the Bn-1 changes from 1 to 0 till not, the output of the T flip-flop will not change. Okay, so first it is connected to 1, so this is the negative ramp, so this will be 0. Okay, so V1 is reset to 0 due to the inverting integrator, this will be 0. So if this will be 0, then VC should be 1. Since the positive analog input voltage is connected to the inverting input of the integrator output V1 is negative ramp. This is the negative ramp. While the comparator output VC is positive and the clock is passed through the AND gate. And this result in counting up the 4-bit decade counter. This is counting up. Initially at t is equal to 0. Initially as t is equal to 0. The Q is 1. The Q is 1 initially. The Q is 1. Switch is connected to V. The output of integrator is minus 1 by RC. RC is the time constant. R and C, 0 to 2 V in dt. So that's equal to minus 1 by RC V in dt. So V in into T, where RC is the time constant of the ramp generator circuit. If the input voltage is positive, then the output of the integrator is negative or V1 less than 0. Due to VC is equal to 1. Now the n-bit up counter will be starts counting in up direction. Due to the clock is ended. This is 1, this is 1, this is 1. So the counter is will count in up direction. The moment V1 tends to go below 0. The clock pulse reaches the clock input terminal of the counter, which is initially cleared to zeros. First is initially cleared to zeros. Okay. So the counter begins counting from 0002 to 0001. And this process will continue until the last clock pulse. That means 2 to the power of nth clock pulse will not come. And the output of the counter is all 1. Till now, the counter will start counting in upwards as a up counter. Up counter means it will count in increasing manner. 0, 1, 2, 3, 4, 5 like that. At the 2 to the power of nth clock pulse, at the time of t is equal to t1, the counter is again cleared. The 1 to 0 transition of the MSB of the counter sets a flip-flop that controls the state of the switch S, which now connects the integrator input to a reference voltage of the polarity positive or polarity opposite to the analog input. That means the minus VR. When the 2 to the power of nth clock pulse will come, the counter is again clear. The 1 to 0 transition of the MSB of the counter occur, and it sets the flip-flop that controls the state of the switch of the S. Set of the flip-flop means this is input as 1, so then it will be 0. When it will transit from 1 to 0 at the 2 to the power of nth clock pulse, 1 to 0. So then this transition occur. Then the flip-flop is set as the logic input is 1. So then the Q will be 0, and the switch will connect to the minus VR, which is the opposite polarity of the input voltage. So at t is equal to t1, where t1 is the 2 to the power of n into tc, then the v1 is minus 1 by rc v in into t, where t is equal to 2 to the power of n into tc. So in the next clock output of the n-bit counter is all 0 again. This will trigger the t flip-flop, and the output of the t flip-flop will change to 0. It means the input of the integrator is now minus VR at t is equal to t1. This is the logic, and this is the mathematical expression how the output of the Q will be 0 and it is connected to minus VR. At the time t is equal to t1, when the 2 to the power of nth clock pulse will come, the n-bit up counter is all 0. This will trigger the t flip-flop, and output of the t flip-flop will change to 0 due to the input of the t flip-flop is logic 1. Now the ramp integrator begins at minus B1 and increases upward until it reaches to the 0. So this is the positive RAM. Okay. So during this time, the counter gets advanced and it will count again. When V1 reaches 0 volt, the comparator output will become 0 because this is one positive RAM. So this is becomes 0. So the clock inhibited from passing through the AND gate. So when T is greater than T1, that means 2 to the power of NTC, what happens? This is minus 1 by RC, 0 to T, minus BR dt. So that is minus BR by RC into T plus K. So again, the T is equal to 2 to the power of NTC. We will write this. So now if we compare this and this, then we will get the value of K. Now if we put this value of K in this equation, then we will get V1T is equal to VR by RC into T minus 2 to the power of NTC by RC into V in plus BR. So now if we take the common, then we will get this. So now if this T1 is nothing but a 2 to the power of N into TC value. So that is put this here 2 to the power of NTC as T1. As T1. Put here, we will get this equation. For T is greater than T1 to T2, the output of the integrator is negative. And its value is increasing. Due to this, output of the comparator will be logic 1. Then the up counter will count in up direction. This process will continue until the output of the integrator becomes 0 after the n number of clock cycles. Okay. How many clock cycles are there? That depends upon. So at the time of T2, the V1 is 0, V1T. So we can put here and we will get this equation. Similarly for this equation. So the N is equal to, here the T2 minus T1. What is the value of this? Now N into TC. N is the number of clock cycles. And this is the clock period. So this is the total time. So at that time, we will write T2 minus T1 is equal to NTC. So N is equal to like this. So N is nothing but the binary equivalent of the digital output. So it directly proportional to the input voltage. VR is known to us, 2 to the power of N also known to us because N is the number of N bit up counter. How many number of bits up counter is used? That is called the small n. And capital N is the binary equivalent of the digital output. So here we will get the digital output. There is two slope. One is negative slope when it is connected to V in, the integrator output, and this is the positive slope where the integrator output slope is positive, connected to minus VR. Okay, so minus of minus VR, that means plus VR. For this reason, this is the positive slope. Here, this is the minus of minus VR, minus of minus VR by RC. So that's equal to the plus VR over C. So this, for this reason, this is the positive slope. For this reason, this is the positive slope. So the V in also can be written as V in is equal to VR into T2 minus T1 by T1. From the above equation, it is clear that the unknown analog input voltage is proportional to the time period T2 because VR is known reference voltage and T1 is the predetermined time period. Also, the contents of the 4-digit decade counters at the end of the conversion reflects the 2 to the power of NTC plus the NTC. This is the total time, the conversion time. So this is the 2 to the power of NTC and NTC. This is the 2 to the power of NTC. So this is the total part of the ADC and the DSC.